Hello and welcome. I am Dr. Pauline Fu. In this video, I will present how do you assess a distribution is normally distributed. So by the end of this lecture, you will be able to use normality probability to assess normality. Suppose that we obtain a simple random sample from a population whose distribution is unknown. Many of the statistical tests that we perform on small data sets require that the population from which the sample is drawn is normally distributed. Up to this point, we have said that a random variable x is normally distributed, or at least approximately normal, provided that the histogram of the data is symmetric and bell-shaped. This method works well for large data sets, but the shape of histogram drawn from a small sample of observations does not always accurately represent the shape of the population. For this reason, we need additional methods for assessing the normality of a random variable x when we are looking at sample data. Normal probability plot. This tool can help us to assess normality. When you plot normal probability plot, what is your x? Your x is the observed data, okay? And your y, and we are going to use a formula to calculate a new y so that we get normal probability plot. We hope the result will be similar to a straight line. Okay. So a normal score is the expected z-score if the data value on the random variable is normal. The expected z-value of an observed value will depend on the number of observations in the data set. So how do we draw a normal probability plot? We based on the following steps. Step 1, arrange data in ascending order from smallest to the largest. Step 2, compute Fi equal to I minus 0.375 divided by n plus 0.25. What is I? I is the index. It is the position of the data in the ordered list. For example, if you have an ordered data list, so from the smallest to the largest. Suppose this is the data list. What is I? I is the position of each data. So number 2, the I for number 2 is 1 because number 2 is in first position. I for number 5 is 2 because 5 is in the second position. So those are the I indicate the position, okay? So number 6, I equal to 3. Number 9, I equal to 4. Number 13, I equal to 5, okay? So I is the index indicating the position of the data in the ordered list. N is the sample size. So in this case, 1, 2, 3, 4, 5, N equal to 5. And the expected proportion of the observation less than or equal to the I's data, that is Fi. We calculated here, Fi. So Fi represents the expected proportion of observations less than or equal to ith data value. Step 3, find the Z value based on Fi from either the table or from Excel. So remember in step 2, you get Fi. So Fi is actually the area. So this area represents Fi, because this area represents the proportion of the observations that is less or equal to the ith data set. So once you have this Fi, in step 3, you need to find out what is this Z value here. In step 3, find the Z value. We did this in the last lecture, okay? And then step 4, plot the observed value on the horizontal axis. So observed value, for example, this value is X on the horizontal axis, okay? And then corresponding expected Z value on the vertical axis. The result of step 3, the Z value as the Y-axis. Okay. And you hope to see the straight line here, or approximately a straight line. If it is a straight line or approximately a straight line, that indicates the data from normally distributed population. So I already explained this one. So the idea behind finding the expected Z value is that if the data comes from a normally distributed population, we would predict the area to the left of each data value. The value Fi represents the expected area left of the ith observation when data come from a population that is normally distributed. So for example, F1 is the expected area to the left of the smallest data set. F2 is the expected data to the left of the second smallest data value. So anyway, Fi represents the area. So this area is Fi. And this point is Zi. Z value, okay. If sample data is taken from a population that is normally distributed, a normal probability plot of the actual values versus the expected Z-scores will be approximately linear. Okay, so when you use observed data as X and you use the Z-score as Y, how do you calculate the Z-score? See, okay. Step 3, you get this Z-score. How do you find this Z-score? Based on step 2, based on this area. Based on this area, you get the Z-score. Once you got the Z-score, put in the Y-axis. And the result, you should get an approximately linear. It is difficult to determine whether a normal probability plot is linear enough. Basically, if the linear correlation coefficient between the observed value and the expected Z value is greater than the critical value found in table. Okay, I'll show you, we did this table before, okay? When we did a linear correlation coefficient, okay? Then it is reasonable to conclude that the data could come from a population that is normally distributed. normal probability plots are typically drawn using graphical calculator or Excel, SPSS, SAS, Minitab, and other statistical softwares. Now let's look at an example. Interpreting a normal probability plot, the following data represent the time between eruptions for a random sample of 15 eruptions at the odd faithful geyser in California. Is there a reason to believe that the time between eruptions is normally distributed? So this is the original data. The question is, are these data normally distributed? That is the question. So we can use Excel or graphical calculator or SPSS, SAS, Minitab, etc. to get normal probability plot. So this red dot is the normal probability plot. Okay, looks like they are approximately linear. And this is the box plot. Okay, and if it is perfect normally distribution, the middle, the Q2, the median should be in the middle, but this one is a little bit off. This is Q2 median. And this median a little bit to the left, but it is roughly approximately normal. Another example, okay, for normal probability plot. Suppose that 17 randomly selected workers at a detergent factory were tested for exposure to a Bacillus subtilis enzyme by measuring the ratio of forced expiratory volume to vital capacity. So FEV is the maximum volume for air a person can exhale in 1 second. VC is the maximum volume of air that a person can exhale after taking a deep breath. Is it reasonable to conclude that FEV to VC, this ratio is normally distributed? That is the question. Okay. So those are the data, original data. The question is this data normally distributed? That is the question. Okay. So we can use technology to get probability plots, and those red dots is the probability plots. Okay, looks like they are roughly on a straight line or closely to the straight line. So in summary, what we did this video, we try to assess if the data come from a normally distributed population. And how do we assess this? We do go through a couple of steps. Okay, step 1, we need to sort data in ascending order. And step 2, we need to find Fi. Fi represents the area to the left of a z-value. Step 3, based on Fi, based on the area, we can find a z-value. Step 4, use original data as x and the calculated value as y. You hope to see the results approximately on the straight line. Okay, that's all for this video. Thank you so much for watching. I'll see you next time.